Next topic, segmental lining, grout, backfilling grout. Here, design requirements, more from the practical way, not how to calculate. There are specialists. I'm definitely not one of the specialists how to calculate segmental structural calculations for segmental lining. But what I would like to show you is the design requirements with the interaction with the TBM, as well with the segmental lining options, what you have, and then as well the required quality management later on during the production of the segments, as well then during the operation with the TBM. And then at the last point, I would like just to give you an introduction about the grouting, just the grouting process in general. It all started a long time ago under the River Thames in London, where it was the first shields driven in quite a old-fashioned way. A lot of men working inside the shield, hand excavating, and as well then with a lining practically made out of brick stones. Nowadays we have it a little bit more easy. Instead of 20 people, we have one standing in the middle, acting with a remote control and practically erecting with two helpers the whole segmental ring within 20 minutes. There's as well the pipe jacking, which is a highly competitive and very efficient lining system in itself, but for the purpose of this presentation, I would like to keep that away and just concentrate on this segmental lining systems. So, what do we do? The TBM is moving ahead. Inside the TBM, you have practically the segmental lining, which you erect under the protection of the tail shield. With that, you have here in the back, you have the ring gap, which is excavated by the TBM and supported by the shield. And then you have here the step between the shield and the outside of your segmental lining. And that has to be filled then later on with grouting. In the front, you have the TBM pushes itself always forward by using the last built ring. And with hydraulic jacks, and when these hydraulic jacks are extended far enough, you start then building up the next ring by retracting only 2-3 of those rams, which are necessary to create the space, and then you place a segment in there. Here again, a little bit the description. As you have seen, we are fully extended thrust rams, the TBM advanced for the full stroke. And then you start mostly in the invert with the invert segments, and then building up, retracting the jacks, and then building stone by stone up the complete ring on both sides. Once you have then placed the segment, you thrust again with your push ram. You push it against the last ring and compress with that then the gaskets, so you create then a watertight joint. Here's an example again. Here again the schematic, the shield tail, the thrust rams, the segmental lining, and then you have the geology here outside, the ring gap which was created by the larger TBM, which you have to fill with the grout. And here you can see the brush seals. Those are here the seals here in between. They are practically isolating, let's say, the ring gap from the tunnel intrados, the inside of the TBM. So they are keeping away the grout. Here again, finally assembled shield tail to the TBM with again here the steel brushes for sealing. And later on there comes an erector as well, which then here in that area then places a segmental lining. So for the people, it's practically all the time they are in a secure area. in the front, they have the shield. They are covered by the shield. And within this metal shield, they build up the concrete lining, and thus have full protection all the time. The lining needs to take care of the loads from the surface, from the groundwater and the overburden, so they have to be designed for that. But more than enough, they have as well to take the forces from the TBM advance. And as you can imagine, it has an active phase support pressure, the TBM, which is acting against the direction of drive. So it's actually pushing the TBM backwards. And that is a huge force because it's quite a huge phase compared, even with the small overpressure you have, you create actually quite a big force there. You have the friction of the shields, and then you have as well the advanced force for steering, which you need just to push the TBM ahead. And all these forces have to go practically through the surface here in front of the ramps and then into the segments. So you can imagine doing that. This ring has not that big problem anymore because the TBM, it's already, all the forces are distributed. They are going by friction to the ground, and then the forces slowly disappear into the surrounding ground. So the worst case for the segment, or the hardest loading moment for the segments is right there when they are placed in the segment and the TBM starts thrusting off from that segment. Especially when it comes then to curves as well, because then going around the curve, a lot of TBMs are steering just with the thrust rams. So you have an additional force here just pushing the TBM on one side around, on the outside around the curve, and to control the orientation. So those are practically the most leading load cases for segmental lining design. Additionally, you have segmental lining has to have a sealing capacity for the outside water, because normally you want to have a watertight tunnel. So you need to address those pressures as well. On some cases, we are going up. There were tunnel projects which had pressures up with water up to 13, 14 bars, and that has to be taken care of by the segmental lining as well. And then on more seldom cases, you have an internal pressure, like you have in headrace tunnels, like you have as well in water supply lines, large water supply lines, where you actually then use intermediate pumping stations, which then forward the whole water strength. So you have, on some cases, higher internal pressure than you have on the outside. And that it creates a totally different load scenario again, because then you have to maintain somehow the joints closed of the segmental ring, even when there's high pressure inside. And then, of course, you have some special cases, like in some metro or high-speed railway lines, where you have to take care that the segments are not destroyed by themselves or by the operation due to the electric currencies, induced electricities. So you need on some projects then as well here grounding systems which then protect your segmental lining. Which options do you have? Earlier times we had the cast iron was quite widespread in the early times with TBM tunneling, and the possibilities there were that where you could produce them quite precisely, and you had a possibility at that time to practically close the joints and make them watertight with lead, which you practically pressed into the joints. Those tunnels are still existing in some cities with old metro systems and create now a lot of headaches because they need to be replaced as the lead is starting to disintegrate and it starts leaking again. And it's very difficult to find companies who are still capable of doing that, to work with lead. So typical today are precast concrete segments with a cage reinforcement. You see them here on the left hand. These are typical cages for these, which are placed inside the molds, and then the concrete is poured. And with that, that is practically standard since the 80s. We have now developed further, and more projects are switching over to fiber reinforcement. The fiber reinforcement has the advantage that you do not need to really manufacture a cage or some structural element. You only need to distribute the needles, the steel needles, into the concrete and then pour it together. Practically, you pour the reinforcement together with the concrete into the mold. Sounds easy. It's not as easy. But that is, at the end, it's a very competitive solution, and contractors can save quite substantial percentage on these solutions where it is possible. Larger tunnels have always a problem then that it's not that easy because even the segments are getting very large and you have bending moments in that, and sometimes they are still the requirement that they have at least a light reinforcement cage just to take the bending moments. So, selected the type of lining. Then you start with the production, and you have to start then with a close quality management, because nothing is worse when you start with a segment quality and with a segment design. It's designed for perfect solution for you, and then during the production it has so many problems then created that you have at the end a tunnel which you have to do a lot of repair works after your TBM has finished the excavation. So it's important to have a tight quality management regime. And it's not only that, it starts with the overview that the cages are always the same. They are the required diameters, the steel is the required one, the connections are the correct ones as designed, as specified. And then as well, when you place them into hopefully the correct mold, that as well you have spacers that they are sitting in the right position, so you have always a cover on top of your reinforcement cages. So there are many small little points which would as well a little bit be excessive here to control permanently and continuously the quality of the segment production. It's not easy. Those pieces are not easy to produce. You see here an example for a big failure, and that is practically when the compaction of the cement, of the concrete did not really work out, and you had practically behind the groove you had a nest where you had no cement and you had only gravel, the aggregates in. So you can imagine if you place here now a rubber on top of that, this gasket, the water doesn't care if that is blocked by the gasket. It just goes below the profile and passes below, and you have a leaking tunnel, and it's very difficult for you to stop then later on when this segment is placed to stop this leakage later on, because you have to do all the injections around the ground and practically seal the ground around, make a plug around it. And so you can save a lot of time and a lot of money if you have a good quality management here. Another thing is what you have to check as well is the quality of your molds. Molds are highly precise steel fabricated forms which are opened for the production of every single element. They are opened, closed, they go through different temperatures, so they have some wear as well. So in regular instances, you have to control as well the quality of your molds themselves. And you, most of the time, have to readjust them and make them again to the correct measurements, but those can be done by the molds, but you have to keep that in mind. And then, of course, something like that you even don't, that is a clear indication that you have a serious problem with your mold and with your concrete to have because this creates later on when installing the segment inside the tunnel, big problem. That's where we come to. Now we are inside the tunnel. We are inside with the TBM operation. And you have to install, in principle, the segmental lining has always to follow the tunnel boring machine, independently where the machine goes. If right or wrong, you need your lining to follow the TBM because you cannot lose the contact. And so it's very important to measure the space between the segmental lining of the last ring and the shield tail. And with those measures, you calculate practically the orientation, the ring orientation of the new ring you want to place. So it follows practically the TBM in its course. If you don't do that, and if you lose practically that space, because then if you erect your segment into a different direction than your TBM is moving, you are closing here that ring gap. And when you close that ring gap, you get into contact and direct physical contact, and the shield will always win that fight because the shield is squeezed in by the surrounding ground. It is highly ductile material. It survives. What happens is the segment will crack, and you will again have a big problem with leakages later on. So it's very important that you take care that you measure the spaces inside, and then that you place it in the right orientation to follow your TBM. Another one is, as well, in the interaction between the segmental lining and the TBM, the erector has certain forms, cones, to practically not only lift the segment, but as well to move it laterally and apply forces to compress the gaskets. If those cones, which are setting in here in this hole, are not really adjusted to the design and vice versa, you will then have a lot of these spalling of the surface concrete. Something most clients don't favor as well if you produce one segment after the other and it looks always the same. So those have to be adjusted as well and should be part of your quality management system. And then as well, another thing is squeezing, as I said, especially with the keystone, the last stone in a ring. That one is getting really compressed into the open space, which is reserved for it. Sometimes it's not large enough, sometimes it is. And then it is a good idea to facilitate for the gasket to slide on the other gasket. And that's what you can do practically to facilitate it a little bit, is to use, for example, soap or something that you just have the possibility to facilitate it for the gasket to get in. Because this one is now sticking out, and you will build, there's a next segment, here's already the first of the next ring in. You will then come here and have to practically compress here again this outstanding gasket, and it will not be in plane with this one because it's too much material outside. So again, a weak spot in your ring building, and again a problem then later on which might end up with leakages or even cracks. And that comes then to the packing, because that is then used a lot by contractors to use packing with plates in between to compensate then for the differences in your plane of the last segmental lining, to compensate that somehow. And then you start building that up, and theoretically it works fine with different thicknesses of the plates at the right positions. You can build this up, but typically on job sites, you don't have those always at hand in the right dimension, at the right spot, so you just put something in between. And so at the end, it is mostly that you end up with continuously packing somewhere, somehow. And that creates then for the whole time big problems for it. Makes the people waiting a lot. It takes a lot longer time to build than those rings. And as well, the quality is not improving. Sometimes it's just better when you just let it crack. 1 ring, 2 ring, and it cracks, and then it compensated by itself, and then you go again and start with, and it cures practically itself. Here's something like that. That is one thing as well, into the extremes, when you see then already with a packing here in between, you saw then that everything is practically spalling off. You can even see the gasket in behind, so you know there's it will leak for sure. And the same problem then that you don't get the bolt in the right position. You can't get it in because it is moved away from the other segment. So that's why it's tricky. Yes, so that is again as well and another point which is practically against the packing is if it is not foreseen by the design, you have a big problem because you actually open up your design gap with the high pressure. So if you have here, let's say, that you have the gap here, the maximum gap, instead of 5 millimeters, you have it up to 7. You see that how it decreases your water tightness. So it has more than one effect. And then there's another problem, which especially with larger TBMs, especially in surrounding ground, which is quite tight and which does not let the water of a standard component bleed out. That you practically observe that behind your TBM, the segments suddenly start lifting up and rising. And you get steps here in between. You get as well here this stepping all over with a slight disorientation of your segments, which then results in, later on in a difficulty in steering and keeping the TBM steered because it's everything wobbling around a little bit. Here's an example. You can have up steps for design 4.5 centimeter step between one ring and the other. And if you go with these 4.5 centimeters measured, you go to your design and you say, well, I have a design, segment design with tongues and grooves. And the design typically gives you 2 millimeters of movement and you have 4.5 centimeters moved, then you know what happened. And it's, again, damage to your water tightness. So here is an example of a road tunnel which was ready to be opened, but only they had here a couple of spots where they actually could not get the water tightness as required by the client. And so even the ProMat plates, the fire resistance plates, have been left out just to do injection and drilling to seal it off. So it's, what the message is it is very important that you take good care as well for the installation process of your segmental lining. Even if the segments are cracking right away, evaluate if it's not better for you to take it out, because you save a lot of time, not in that, probably in that ring installation, but later on until you finally can open the tunnel. You'll save a lot of time because your repairs are reduced. So, ring uplift with the gap. I got a little bit distracted. That brings me directly to the back grouting system. When you have the ring grouting system, when the system is not working really in a controlled manner, that you have an unequal filling of the gap. you have then as well an unbalanced loading or embedment in the surrounding ground. So you get higher bending moments, which again then can produce cracks or other stuff, leakages. So if you have, for example, here, I just pick it out, you leave that corridor and you get a higher pressure than it was anticipated. You had as well, you can have, as this is shown here, it was close, this keystone, which was close to one of the outlets, and the pressure suddenly increased higher. That one actually moved inwards. It was completely pressed inside. And so it was sitting like 10 centimeters in, and so it was, they had to use then steel brackets just to hold it in position, and then later on to make us repair. So it's important that you keep the parameters even for the grouting system under control. For smaller TBMs, it's not that easy, because smaller TBMs are often still using an old technique as the injection of the grout with, through the segments with a hose, when all manually controlled. So they inject as much as possible here, and then they go to the next step and have it then on the opposite position, and it's never continuous, to say, for the full circumference. It's always local injections at local spots. But that is due to the fact that with the small machines, you have as well small shield tails, which have not the space then for embedded grout lines. Preferable is, of course, the continuous grouting system through the shield tail with a row of pumps, which are continuously supplying all grout lines at the same time. This way you can then really guarantee that all the material, the embedment of your segmental lining is as good as possible. Here's an example from a shield tail waiting for its TBM with couple of lines. They are a lot of lines here on the top out of different reasons, but with a real good number of ports for injection. And that way you can really be sure that it distributes along the ring gap. Two-component grout is, I would say, by now one of state-of-the-art to use two-component grout. It has the beauty that you have liquid materials which you can store for a long time. It's not like cementatious grout, which you mix up and then you have to use it in the next couple of next hour. You can store that. You have tanks, holding tanks on the TBMs, and you can store them for long periods without let's say, reducing the quality. And only once you start mixing them together, the A component and the B component, then they start to react, and then it's fast. Here's an example of the increase in strength. You have here the A liquid, which is, let's say, the base material, and then you have the B liquid, which is, here in this case, a sodium silicate-based accelerator. You mix them together, and within 5 to 10 seconds you have then a gel, created a gel, which is still pumpable, and then after that time it gets into a plastic consistency, so it's at rest, it's already strong, but still you can pump it as you need, and that is still for a long time, which is quite substantial. And only after that, then it starts getting solid, and it creates within 1 hour quite a nice and strong background for your segmental lining. So it actually combines the beauty. It's easy to handle when you don't need it. You have lines even going for kilometers through the tunnel where you just pump from surface to the front to the TBM. And when you need it, it reacts fast. And that especially, as I mentioned before, with the large TBM diameters, it's actually a good solution because that prevents then that in any type of material that you actually can fix the ring in its position when it comes out of the TBM, and you really reduce this lift ups behind the TBM. This is a schematic of the installation per injection port. It looks quite substantial. You have here practically 4 tubes. Well, the one is the pipe with the A component, with the base component going here to the outlet. That is the port, and here practically starts your ring gap. And you have the A line going there as a big line. And then you have the B, the accelerator line, going through this valve and then mixing up here in this position, and then as well going outside. You have here a large valve which practically controls the complete system. It can stop here and isolate the whole internal system from the ring gap, as well as it can stop here your flush water line. It moves back here then the valve and closes the line, which you can use then for flushing. I can show this to you. This would be during the start procedure. When you start with the TBM advance, you practically pump only the A material to start in this gap. And once you have then advanced and you see that the TBM is moving on, you then open up the accelerator line with this valve here, and it here mixes up with the base component, and then you have practically a hot material, hot grout going inside, and it starts reacting right there according to the time schedule which we have just seen. So if you are stopping, you again first switch off then the accelerator. You still flush a little bit with pure base material, and then later on you stop the TBM, you move this valve and close the complete system to the outside, and then you can back flush practically the whole system. This way it is guaranteed that you actually have a quite clean arrangement. And the first systems were coming on the market, that was always a big problem, that they easily got plugged, and you were then trying to clean in the shield tail these pipes, which was kind of a complicated situation. Here are examples for the operation table. Obviously, each line, the pumps need a certain minimum flow. So you have here the examples for the TBM advance, and then as well for the volumes you can pump through, and then the numbers of pumps which should be running. That is the control panel for it. Normally it is automatically steered, and it's only important that you practically do not miss the point before you come to an alarm, before you stop, that you already start then with the closure of the accelerator, so you are sure that no accelerator, no hot grout is here inside this part. With that, thank you very much.